So welcome. I'm painfully aware that I'm standing between you and alcohol. So I'll try and keep it to the three or so hours I've got planned, yeah? We're all good for that. So I'm going to be talking about this idea of software architecture as code, evolutionary architecture, and hypothesis-driven architecture. I've used these words very specifically in this title. I'm going to be unpacking these as we go. But first, if you ever wondered what it was like to be on one of these sort of sway stages, doing a talk at NDC, it's a bit like this. Actually, this is the Parliament chamber in Star Wars Episode 1, and it kind of feels a little bit like this being up here, kind of stuck in the middle with this amazing bank of people rising in front of me. Okay, ha ha ha. So as I say, I'm talking about betting on software architecture as code. But what is software architecture? That's my first question. And I'm going to be using this definition from Martin Fowler, which is that software architecture is those decisions which are both important and hard to change later. Important and hard to change. It could have been by someone else, could have been by Ralph Johnson. Unsure at this point. So what are the things that traditionally have been hard to change in software architecture? Well, I would argue that there's a bunch of these things, right? There's things like programming languages. There's things like domain application protocols, so how we organize the state of our system as they're communicating to implement business processes. The process boundaries themselves of the components, the services that we're building. How we integrate, what choice of protocol do we use? Are we going to use RPC? Are we going to use RMI? Are we going to use DCOM? Are we going to use REST? And then there's the hardware environment and the deployment topology that we're going to be running our software on. Now, these are things that traditionally have been hard to change. But I would argue over the last few years, they've become much easier, much more malleable, or at least a lot of these things have. So what happens to how we think about our software architecture when some of these things that we hold to be true, our sacred cows, are not true anymore? And we kill our sacred cows. What happens if these properties, these characteristics, actually become easy to change? So what do I mean by that? Well, programming languages. I once saw a great talk by a guy called Chad Fowler about his time at Wunderlist, where they had a view that if you were building a microservice, you could choose any language that you liked. They had Ruby running, they had Haskell running, but they had some guardrails that said if you choose any language, you must be able to rewrite that service in a day, and you must be able to read it if you don't know what that language, if you're not a programmer or an expert in that language. So with the advent of things like microservices, decomposing our systems to smaller systems, I would argue that programming language is something that is now much easier to change. Same with process boundaries. Right? They are much more malleable these days. We can split things, we can merge things. I'm not saying it's for free, but if we create things small enough, the size of my head, if you know that metric, if we create things small enough, we should be able to change these things very easily. Similarly with hardware environments. Now, gone are the days, if we're thinking about a cloud-native world, gone are the days where we have to wait 9 months to get a new environment provisioned in our data center. We don't need to raise a ticket now with ops. We don't need to do that anymore. We can spin up whole new environments from a command line. So our hardware environments are now easier to change, often just with a few lines of code, infrastructure as code. And similarly, our deployment topologies. So you've probably come across the idea of a Phoenix server. So this is the idea that we don't update our servers, we just turn them off and replace them, then turn them off. But similarly with things like Phoenix environments, the ability to just turn off an entire environment and move it somewhere and start it up again. So these things have started to become much more malleable. And I think that allows us to make different decisions about what we do with software architecture and with our hardware architecture as well, our deployment topologies. But first I'd like to ask a question: how do we normally make decisions about these sorts of things, software architecture? And I think, when I'm in a position where I'm helping teams, advising teams, coaching teams about what a design might look like for the future, I rely on my experience, right? I've been doing this for about 20 years, just over. I've got a grey beard, both definitions. So I've been doing it for 20 years, and I have an actual grey beard. So we do stuff based on our experience, which is great, right? And that's a good thing. until we come up against biases. You know, there's something called survivor's bias or survivorship bias. Just because we did something and it worked the last time doesn't mean it's going to work the next time. So, you know, experience is good with some caveats. We also make decisions based on our gut, right? This feels right. And actually, as we get more experience, our gut feel becomes better. This is down to something, it's actually down to brain chemistry. There's a thing called the Dreyfus model of skill acquisition that says, as you gain experience, you become more insightful. You make decisions in an insightful way. Often that's characterized by not being able to explain why something is a good idea, because you're driven purely on insight, which is great, because it demonstrates a level of experience. That's a good thing if we do that. But again, survivorship bias, if those experiences have led us down one direction, we might be biased in the decisions we make. And we often make decisions up front, still. There's been a big movement, obviously, towards agile, lowercase a, agile software development and lean product development. But most of the organizations, many of the big organizations I find myself in as a consultant, they still have big teams of enterprise architects, big teams of solution architects who are thinking really hard about stuff up front. And this is often, I think, as a result of things going wrong in the past. Oh, that thing went wrong, that project didn't work out. That must be because we didn't think enough about it, so let's think more. And so you get into these spirals of thinking about stuff too much, I would argue. And I would argue that all of these are kind of, you know, these are useful things. We need to think about stuff. We need to do just enough thinking. We need to use our experience. But what if there were other ways that we could make decisions now based on techniques that have only really readily become available in the last couple of years? So my question, again, at the start is, can we make decisions more systematically, more cheaply, and what would that look like? I should probably point out briefly that I work for a company called ThoughtWorks, full disclosure. We're quite passionate about sharing, hence me being here in Oslo today. And I'm probably best known for the work I did with Martin Fowler on defining the original definition of microservices. So this is not really about microservices. So if you came to listen to me talk about microservices, there's a little bit of microservice stuff, but not much. Okay. I'm a big believer in the power of stories. So the rest of this talk, I'm going to be exploring a story, telling a story about the time I worked on a platform replacement for a big science publishing website. It's worth about $3 billion a year in revenue, so you know, pretty good money. But unfortunately, over time, it had become unmaintainable, and ThoughtWorks were hired to replace it, or replace the platform. So I'll be telling that story. I think stories are important. I think we don't share enough stories in our industry. In fact, my former colleague Simon Stewart has this lovely idea that every team should have his idea of a team shaman. So this is someone who can tell you the story of why things are the way they are. So I'm showing my age now, but he always used to use the description of, you know, some new developer joins your team and looks at your Ant build script, your Ant build file, and goes, "Oh my God, how on earth can you work with this? This is awful." And the team shaman will gather everyone around and will say, "Let me tell you the story of the build." I kind of like this idea. So that's what I'm going to kind of do today. I'm going to tell you the story of how this thing we built got to be the way it was. But I'm going to use a very specific type of storytelling mechanism, and it's in this book, which is called The Endlessly Bifurcating Trousers of Reality, which is a Terry Pratchett reference for those of you who are fans. This is a very specific type of book. It's the type of book that I got into when I was about 9, and it's the gateway drug to Dungeons and Dragons, if you like. It's a choose-your-own-adventure book. So in choose-your-own-adventure books, if you haven't come across these, you roll a character at the start with different characteristics, and your character gets to make choices about certain experiences that you're undergoing. So you might meet a skeleton and have to fight them, or you might choose to run away. And so this book is about this project I was on. So let's take a look. The lawful good product owners of the publishing house had long lived in awe and fear of their publishing systems. In awe, for they had made a tremendous amount of gold, $3 billion a year. In fear of the time taken to change the software, their slowness and their fragility. A messenger was sent to fetch help from a distant land famed for its mighty wizards. You have taken up this challenge. Now, I should explain what's going on, really. so there'd been this system in place. It was a 15-year-old C++ SOA platform that was basically taking a bunch of content in XML format. This is the way most science publishing works. You've got a bunch of content in XML format, turning it into some form of HTML, displaying it to a user. The problem is, over time, this thing had degraded to the point it was very difficult to make change. It's very coupled, very uncohesive, if you like. And so, given the fact that rate of change in our world is increasing, they needed to do something about this inability to add new features. Plus, also, it was pretty slow. It was run from some data centers in the US, not taking advantage of things like modern techniques, things like CDNs, CloudFront, and so on. Which meant that as China became a thing, and as Australia finally got internet, I don't know if you know this, up until 2 years ago, Australia had the internet delivered on Tuesdays via parachute and USB sticks. It's true. Honestly. But as Australia became a thing, or becomes a thing, as China becomes a bigger thing, it means you need to be more flexible about how you're delivering this content and much faster. The other problem is they had issues with availability. Now, the interesting thing about publicly listed science publishing companies is that their stock price is intrinsically linked with availability. Because every time you click on a link, click on an article, read the article, they charge someone. And every quarter, the CEO will report to the market how many people clicked on links, essentially. And if it was up, that was good, more money. If it was down, bad, stock price shifts. Which is an interesting set of cross-functional requirements to have. So the three goals were availability, performance, and increase the rate at which you can make change. Let's see what happens next. You must save the product owners by rebuilding their website. You start off the project. In the course of discussions, you discover that your goals are threefold: availability, performance, reduce the cost of delay. An enterprise architect approaches you and addresses you. You may use summon walking skeleton or cast analysis paralysis at this point. So as I described, we've got this a greenfield program to rebuild this platform. So how do you start off? What do you do at the beginning of a big program of work, which is going to involve a team of, in the end, it was up to about 150, maybe even 200 people? How do you start? So we could summon a walking skeleton. A walking skeleton is the thinnest slice through your software architecture that you can get going on, like really, really quickly, and importantly, that you can push all the way through into production. So you have an automated build for this walking skeleton, and it's the thinnest vertical slice through. So you can immediately start delivering value. Or we could cast analysis paralysis, and maybe the enterprise architect will go away for 6 months and leave us alone. Well, I should point out, we did have to do some thinking about what this thing was going to look like, and using Simon Brown unapproved diagramming tools, we created something that looked like this. It's not important. Fundamentally, we had a set of facades or adapters that were sitting over a set of external services. We had some mechanism for doing page templating, edge side includes, and we had a bunch of content coming from places. That's pretty much what we had. So, in our case, we thought, let's just get rid of this enterprise architect for a few months, right? So we cast analysis paralysis on him, in which case we're going to turn to page 3. You cast analysis paralysis at the EA. Foolish young adventurer, says the architect. We follow the evolutionary architecture school, and we shall have none of the lawful evil ways of waterfall. The last thing you see before everything goes dark is the architect incanting in a strange voice. You have died, turn to page 1. It was the only organization where the EA was actually also an EA. So it was an evolutionary enterprise architect. So perhaps we'll go back and we'll summon a walking skeleton instead. Your walking skeleton coalesces in a cloud of noxious gases and solidifies as a Java drop wizard application. You reach into your backpack and deploy a content store. Your walking skeleton reaches out its skeletal arms and grabs armfuls of raw XML. What do you want to do next? Transform the XML inside the walking skeleton in process, maybe as a library, some module. Or do you want to use a magic box to create another microservice outside? We'll explore that in a moment. Because this sort of structure, this branching structure, is really what this talks about. It's about the idea of optionality in software architecture and how we can keep those options open, and how we can explore options as we go through the process of building software. This is something I lifted from a biology textbook, actually. It's something called a divergent evolutionary graph. There are convergent ones as well. And this is kind of how I see software architecture and the choices that we make as this graph of possibilities that extend off into the future. And every time we make a choice, we are going down one of these paths. So in this case, we've got one path, which is to transform the content within a walking skeleton. We've then got another path we can follow, which is to create a separate service to transform that content. And reductio ad absurdum, if you go down one path, you get to a distributed system, microservice distributed system. And the other path you go down, you get to a nicely modular, if you're lucky, monolithic MVC app. So really, the question is, how do we as architects or people involved in the activity of software architecture then, on our teams, how do we decide which path to follow? Experience, gut feel, thinking about it hard. But I think there's other ways, which we'll come to in a second. So I use the word betting in this title very specifically, and this is the definition of betting. I think it's from Merriam-Webster. The act of gambling money on the outcome of a race game or other unpredictable event. Now, for me, I think building software is fundamentally unpredictable. That's because the people building the software are what's called complex adaptive systems. We are, ourselves, complex things. Teams that are building software are complex adaptive systems. The organizations in which they build software are complex adaptive systems. And the problem with complex adaptive systems is you can't reduce complex adaptive systems down to a series of very simple, predictable things and then evaluate an outcome and get the same answer every time. By our very nature, the mechanism of building software is unpredictable. Just because of the people, the software, the organizations, the teams involved. So I think this use of the word betting is quite appropriate here. Can we somehow bet on outcomes? Can we place small amounts of money to work out which of these paths are going to be the right ones? Betting on software architecture. And I would say that evolutionary architecture allows us to place smaller numbers of bets. We don't think about everything, design the whole thing. We create a almost unlimited set of options, which we can then explore over time, investing small amounts of money as we go. Whereas I would argue this idea of upfront design, it's the equivalent of betting the house on an outcome. It's basically saying, nope, definitely this is the way to go. Let's stick all our money on red. Turns out casinos make a lot of money that way. This is not new. I'm going to just quickly go back to 1961 here, because there's some interesting stuff happened in one of the biggest programs that was ever run, I guess, by humanity. This is the Apollo space program. Now, who thinks that the Gantt chart for the Apollo space program looked like this? We'll do all our design, build, launch the rocket, go to the moon. Come back for the moon, we hope, and then tea and biscuits at the end. Great. The idea, going to the moon wasn't the aim. It was getting back as well with people in the lander. So, I mean, no, I'm guessing none of us here think that the Apollo program was run like this. Does anyone in the room? No? That's good, because it wasn't, it turns out. It wasn't run like this at all. Because again, this is the equivalent of having this sort of linear path, betting the house on an outcome. And in their case, in the Apollo program's case, the outcome and the way of getting to the outcome were completely unknown. They were answering questions that had never been answered before. So it wasn't this linear path, if you like. In fact, what they did was create a set of questions and then design a set of concurrent experiments, if you like, costing hundreds of millions, billions of dollars in order to reach the outcome and to get the answers they needed. They chose the smallest bets they could, ran experiments to get the outcome they wanted. These are some of the questions that they had at the time, right? So, can we survive in space? We don't know. Can we dock 2 spacecraft? Never been done. We don't know. Can we even get to the moon? No idea if we can get to the moon or not. What are we going to find when we're there, right? Is it cheese? It could be. It looks grey. It could be grey cheese. We don't know. Is it safe to land? How do we get the spacecraft and the people back? So they did think, obviously, but in order to answer these questions, they created a set of different programs that answered specific subsets of these questions. And they ran them in parallel, small bets. So the Ranger missions are my favorite ones. This was designed to answer the question, can we even get to the moon, right? So Ranger 1, which was launched in 1961, blew up. That's the first one. The next one, again, blew up. And this mission is literally like throwing a dart at a dartboard. All they were trying to do is launch a rocket and hit the moon, like crash into the moon. Do nothing else, just crash the rocket into the moon. So the first two failed. Third one got off the launch pad, which is good. Unfortunately, it totally missed the moon. Completely sailed past it. Bit of a fail. And so it went. The next one actually hit the moon. Great, success. Let's try it again. No, missed. Damn. Next one. We hit it, but we didn't get any information. But then 7, 8, 9, repeatedly, they were able to hit the moon and get some data back from the cameras on board. They then had another program, the Gemini program. And the Gemini was designed to answer these questions. Can we survive? Can we dock? Can we get returning spacecraft to land? And then they had the Surveyor missions. And these were designed to answer the question, is it safe to land on the surface? And not all of this worked out, right? They had some crazy paths that they went down, which just didn't work. This is something called the Regalo Wing. This is a hang glider bolted or essentially deployed on a Gemini capsule. I think this is a Gemini capsule. So that was the original idea of how to get this capsule back, is to deploy a hang glider and just glide into land. I like to think there's a project manager somewhere who took a look at that and went, no chance, mate. Anyway, so they didn't do that in the end. But again, it was this sort of evolutionary dead ends that they were exploring, if you like. So it certainly didn't look like this Gantt chart. Going back a little bit further, 45, I won't go into too much detail. This is a great book about the atomic bomb project, the Manhattan Project. At one point on this program, they had 13 then Nobel Prize winners who would join the same poker game on a Friday night. And that didn't include Murray Gell-Mann, Richard Fineman, who came afterwards, got theirs afterwards. It's one of the most amazing endeavors. Unfortunately, obviously with a horrific outcome. And this book, I recommend it, and it doesn't shy away from both political consequences and the human cost. But in this, it's interesting because there's a quote from the guy who was the military liaison who's running the program. General Groves, had to begin building before he knew precisely what to build. He worked from general to particular, from outline to detail. They were doing stuff that had never been done before. And again, the way they did it was to run experiments, and actually to run multiple concurrent experiments, placing the smallest amount of money they could at the time. There are other examples. The Curiosity rover is another example of how to solve the problem of we don't know what an outcome is going to look like. It's unpredictable. So how do we solve that problem? And these things have something in common, right? They're high risk. You might be losing people, losing a war, losing a lander. They're quite hard to test, right? You don't want to lose people because you don't want to test that, really. In the case of Curiosity, you can't use redundancy because redundant systems are too heavy. So you have to use modeling and simulation instead. And it's new science. And how do they solve these problems? Well, putting the person on the moon, it was multiple parallel streams of work, rapid experimentation. Curiosity was simulations and modeling. And Manhattan Project, it was concurrent set-based engineering again, working with imperfect information, simulations, models. The Monte Carlo came from Los Alamos. So when I'm talking about this idea of trying to understand the smallest bet we can place, in the case of some of these, they were massive bets because they were massive problems. That's interesting. Because to overcome these obstacles, they created these options. They had optionality at the future, and they ran experiments to solve these problems, or to address these. So all of these are examples of creating options, placing bets for only the money we can afford to lose. At no point did we say in Apollo, we'll just shoot 3 people to the moon and hope they get back. They were pretty confident that that was going to work out. And it's great for risk reduction. But actually, optionality is interesting as well, because it's even more interesting than this risk reduction approach, taking better decisions as we go. Because it turns out options have a real value. Now, I'm not sure if anyone here has worked in investment banking or does day trading or anything like that. If so, you might recognize this. Does anyone know what this is? No. So this is the famous Black-Scholes equation, which actually proves that options have value. So in economics, this is obviously very important. This is why traders like options, because options themselves have an intrinsic value. You can trade them themselves as an instrument. And the fun thing about this is volatility plays a massive part in this equation as a term. The idea that in volatile markets, options actually have more value, which is interesting, right? This is why, of course, any trader you know is like rubbing their hands at the whole cryptocurrency thing at the moment as everything's going up and down, right? Someone somewhere is making a tremendous amount of cash off the volatility in the cryptocurrency markets. But how does that apply to what we do? Well, I would argue that the half-life of software that we build, the tools we use, the techniques that we apply, it's actually coming down, right? Things are changing at an ever-increasing rate. Not only that, but the markets in which we find ourselves are changing more rapidly and more rapidly. This is a little slide from a deck I have on our ThoughtWorks technology radar. And in this, Docker only appears sort of up here somewhere. Right? This is our view of what's interesting and going on in the industry at the moment. We didn't even have containerization back here, right? Functions as a service didn't exist, although obviously we had database triggers, but that joke must have been made at this conference already. Stefan Tilkov said, it's great, we've got functions as a service now, which is database triggers in the cloud, awesome. You also made another observation about distributed ledgers, which is really good. As an industry, we've gone from strong consistency guarantees to eventual consistency guarantees, and now we've ended up at no consistency guarantees at all, right? Which is fun. So, actually, by creating options, we're doing a number of things. We're able to reduce risk, but we can also take advantage of the fact that things are moving really fast. Right? So these things themselves intrinsically have value. Back to the story. We're going to use a magic box. You throw the magic box in between the walk-in skeleton and the content store. A villager approaches and exclaims, "This beautiful content I see in front of me seems to take an awful long time to get here. You must somehow make the content arrive faster. If you have a HTTP cache in your inventory, you may use it now." And again, we've got options. So what we've done here is create a separate microservice to do the XML to HTML transformation. We're using, I would argue, the best functional programming language. Don't let anyone tell you that F# or Haskell or anything is. We're using XSLT to do that, because why wouldn't you? So that was doing a little transformation. And then we were returning HTML, which was being assembled edge side, if you like, by a templating service, which was the original walk-in skeleton. Kind of looked a bit like this. A bunch of XML and S3, some expensive service running lots of XSLT transforms, and edge side includes and templating with other stuff. Now, our requirements for performance were these: 0.8 seconds time to first byte, and 1.5 seconds for page load, and this was at the border of China, essentially, as well as in the US, Europe, except everywhere else. Which, that's pretty reasonable requirements, you'd think. So when we first started running performance tests on our walk-in skeleton, so we were in a production-like environment, we were able to run performance tests. We weren't live. There's a difference. We weren't getting real users accessing our system, but we were able to run performance tests on a production-like environment. And it turned out we were running at about 35 seconds for page load. Now, there was a great talk earlier about quantum computing. There's a lot of maths in that. I didn't really get much of it, but even I know that 35 is more than 1.5. Which is bad in our case, right? Because we're blowing our requirements way out of the water. So we thought, hey, well, let's add a cache at some point in this. So again, on our branching divergent evolutionary graph, we've detected some performance problems. What options do we have for the future? Let's just add a cache. But where do we add the cache? Do we add it in front? Do we add it behind? The other problem with this is, if you've ever worked in publishing, there are different types, clearly, but if you're in news publishing or magazine publishing, the content that you're providing is eminently cacheable, right? Most content is going to be accessed shortly after it's been published. So pre-caching that is kind of a pretty sensible thing to do. Unfortunately, in science publishing, you may be as likely to access something from 50 years ago as from a month ago. So you've got this vast repository of data with a very sparse access pattern to it. So we were living in a world where instead of cache hits predominating, like in newsprint or whatever, we were living in a world where cache misses were going to predominate. So that would mean we'd have to pre-cache everything, right, which you can do, but there's terabytes and terabytes of this stuff. So that's a big job to do. And as we know, there's the old joke, 2 hard things in computer science. But there is a bonus joke on this. Did you know that there are only 2 hard things in messaging? Right, if you knew this one. 2 exactly once delivery, 1 delivery order. Yeah, you get the joke. I mean, the point about caching is, yes, it's not a difficult thing to do, but actually you have to think quite hard about the type of data you got, the access patterns, where to put this stuff, as will become clear later. So, let's just add a cache, said no one ever. I'm going to take a little sideways step now, because the subtitle of this talk was a note on hypothesis-driven architecture. So that's the bit I'm going to kind of talk to you now. I'm guessing a lot of people in the room will know who this guy is. So this is Richard Feynman, famous Nobel Prize-winning physicist. And he's got what I think is the most succinct, probably the best definition of the scientific method that's out there. It's from On the Character of Physical Law, which is a series of lectures he delivered. I think it's at Stanford. The videos are actually online, pretty grainy, and so are the transcripts available from Stanford or in book form. And he said this: in general, we look for a new law by the following process. First, we guess it. And this is, he's Nobel Prize winning. He's talking about guessing, all right? This is interesting. Then we compute the consequences to see what would be implied. Then we compare the results of that computation to nature, to experiment. And if it disagrees, it's wrong. He says, in that simple statement is the key to science. If it disagrees with experiment, it's wrong. And I like the way he goes on to say, it does not make any difference how beautiful the guess is. It does not make any difference how smart you are, who made the guess, or what your name is. But if it disagrees with experiment, it's simply wrong. I quite like that. You take subjectivity out of this. It's not about James, who's got 20 years of experience. And this is also about me standing on stage. Don't take my word for all this either. It's about what are the experiments we can run, what are the hypotheses we can state. So to break this down, I'm going to go through what I think we need in order to run experiments to enable us to choose the best options for software architecture decisions. So we need to do a few things. We need to be able to observe nature, make a guess, compute the implications of that guess, and compare them with nature, and then see if it's right. Let's draw a conclusion. So for our software systems, what do we need to do this? So I think we need observable systems. Observability, yay, it's the new thing, right? We need to be able to think, that's good. We need the ability to deploy small changes, not just to features, not just to add new features continuously, but to be able to deploy small changes to the way we structure our software, the way we deploy, the way our hardware topologies, deployment topologies. And we need the idea of some lightweight probe to tell us whether we're making the right decisions. So I'm just going to run through quickly the practices we used on this project to enable us to take really small decisions, place small bets. So the first thing was good monitoring. And I'm going to use Dan North's, if you know Dan North's definition of what monitoring is, because it's quite an overloaded term. So Dan uses this definition. You need 5 things, essentially. You need instrumentation. So your software needs to be describing what it's doing. You need telemetry. That information has to get to you somehow. You have to gather your data. You need to be able to visualize that data in a meaningful way. You need to be able to take action as a result of that data. And then if you're way down the road, you can do predictive alerting and cool stuff like that. But really, it's the kind of first three things we need for our idea of observability running experiments, I think. So what do I mean by observability? So in this case, we had a ton of stuff in place delivered from libraries. So we were measuring request latency. We were looking at service health, both of the services themselves, but also of their downstream systems, so your downstream dependencies. We were looking at OS metrics, hardware metrics, and so on. And we were also doing request tracing. So we knew end-to-end the impact of requests and where they were going. And the tools, this was a few years ago now, so the tools are looking a little dated, I will admit. There are newer versions of these around. But we were using like Graphite, Hystrix, CodaHail metrics. Dropwizard comes with a lot of this stuff in Java. We're using Chaos Monkey to do chaos engineering. We're using Breakerbox in Yammer. And this is some examples of some stuff. So this is our Graphite Dashboards. One example of our Graphite Dashboards showing, what's this one showing? Oh, this is showing XSLT transformation times. This is our Hystrix dashboard, showing all the circuits that we had in our system. So we had the ability to understand what's going on. We've got data, we've got observable systems, we can visualize this information, which is good. So how do we now make small changes and roll them out? Well, we know what the answer is to this already, right? So things like continuous delivery, this has been around quite a while now. These are the three monkeys of continuous delivery. This is Jez Humble, Dan North, and Sam Newman, with Dave Farley popping in because he wasn't at that dinner. I won't go in too much detail about build pipelines and continuous delivery itself, but suffice to say there's a lot of knowledge out there. The book is canonical, clearly. But put simply, the idea is when we commit our code, that code is migrated through a series of stages in a pipeline where we apply progressively more testing to it, which becomes slower as the surface area of test increases. The idea is we get more production like one end, and we get faster feedback if we find test failures the other end, which is good. And we've been doing this for our features for a while, for feature development. But what we haven't been doing for a while, well, for that long, is the idea of having build pipelines for your infrastructure code, which is automatically tested, deployed, and so on. So if we apply that same idea to things like our Ansible playbooks, to Terraform, all this stuff, then we get the ability to continuously deploy, continuously make small changes to things that were previously difficult to change. And the idea is we want to be able to do this go around this loop in minutes, ideally. So make small changes, form a hypothesis, make a small change, work out whether our hypothesis was valid or not. So then the idea of having a lightweight probe into your system comes in. So what do we mean by that? So what we were using were really, really simple performance testing tools. So not the kind of bees with machine guns and Locust and Gatling, JMeter, the heavier ones. Just really, really simple, lightweight tools to run simple performance tests. And again, when I say performance tests, I'm not talking about all of the complexity. I love performance testing. It's one of my favorite subjects, so come and talk to me about it if you want. But we weren't doing any of this stuff, SOAP testing, compressed SOAP testing, stress testing, high load. We were later, but not for these experiments. Instead, we were using this idea from our radar again of simple performance trending. So having a test that runs for about a minute every time you commit some code, either functional code or in your infrastructure code. Well, that means if it's only a minute, it can sit either in line in your pipeline or off to the side, and you can trend over time what's happening with performance in your systems, which is kind of very useful. So the tools we were sort of using or looked at and then discarded and then used others, we started off with Apache Bench, really, really simple. It's the HTTP server's benchmarking tool. It's literally a command line. You can stick that in any build script, right? We then moved on to using Siege. Again, command line tool, really, really simple. And actually what we ended up doing is using a combination of Siege and Vegeta, which was at the time, it was a pretty new library written in Golang. And the nice thing about Vegeta is you can specify a constant rate of requests per second. So rather than say, hammer this endpoint for a minute as fast as you can say, just send 2 requests a second to this endpoint. And the reason that's nice is you can use that to measure the latency. They're like tracer bullets. So you don't measure latency of the thing applying load, you measure latency of the thing that's firing tracer bullets. So simple, lightweight performance tests. We've then got the idea of the cloud-native infrastructure as code. Now, one of my colleagues wrote the book, Infrastructure as Code, Keith Morris. Again, another great book. And the idea of pipelines for infrastructure as code. So what sort of stuff were we using? What tooling? So we were on Amazon, AWS. We were using Botto to talk to the Amazon APIs. We were using Ansible and Jenkins to do our deployments. But we also used or took advantage of a set of other tools and techniques. The first one was the idea of a Canary Release. So releasing something, but then not making it live yet. So being able to work out whether the thing that you've deployed is working in the way that you expect. We use this a lot for A/B testing, I know. We were using it to run these experiments. We also use this idea of Phoenix environments, and not just a server that you can just replace quickly rather than upgrading or deploy onto, just turn it off. But also environments, so we could take a whole production environment and start it again somewhere else, just with a simple 2 or 3 line change in our scripts, in our infrastructure code. And then we would use taking advantage of blue-green deploys as well. And this is an animated GIF, actually, of a DNS switch between old and new versions of a set of services on this project. And the interesting thing here is we're taking advantage of this idea that production these days is no longer the same as live. So they used to be exactly the same thing. They used to have the same meaning, right? When we're in a data center, we'd have a production environment which we'd install a new version of our software into, and then it would be live. Well, for cloud native, we don't have to do that. We can take advantage of the fact that we can bring up as many new versions as we like, or as many environments as we like, until our money runs out. And until they're getting actual traffic from real people, they're not live. But they're in production, if you like. So this is good. We're in a good state, right? We've got good monitoring, observable systems. We can think, we can deploy small changes, and we can use lightweight probes to work out whether those changes are meeting the results, or are giving us the results we expect or not. So the remainder of this is about putting it all together. Or to paraphrase The Martian, I'm going to have to science the shit out of it. So this is where we started, if you remember. 35 seconds for page load, and we needed to bring this down to 1.5 seconds. And we had this set of options. I've added a third. We can cache in one of 2 places, but we've got another option, which is maybe we just need a bigger boat. All right? XSLT is quite expensive, often, so maybe we're hitting the limits of the instance size that we were using to run those XSLT transforms. We've got this other option. So which is the cheapest to run an experiment on? Well, we chose the CPU option first. And to do that, we ran through that loop. So we observed nature. We worked out where our current performance was. We formed a hypothesis, made a guess. XSLT is expensive. And then we computed the implications of that guess. Perhaps if we increase the number of CPUs, that would help. And then we compared the results with nature or experiment by running a simple performance test using lightweight probes. And then we drew a conclusion. And it turns out it was a pretty good conclusion. We were CPU bound. We came down to about 6 seconds for page load after implementing that small change. And bearing in mind, it's infrastructure as code. So that small change is a single line of code. All right? It's give me a bigger instance, please, Amazon. Something that would have taken months previously is minutes or seconds even. Right. So the second guess we made, because we'd made a bit of a we'd been a bit naive, to be honest. The second guess was maybe we should move compute to where the data was. We were using, well, all the XML was sitting in S3 in the US region, but all our compute was running in one of Amazon's European regions. Now, it doesn't take a genius to work out going across the Atlantic every single time you need to get some data is going to add some latency. It's about 200 milliseconds, in fact. I think it's about 100 every time. So let's, again, make that guess. Let's move compute to the data. And when we did that, we brought down our latency to about 4 seconds. Our third guess, and again, we had instrumentation around the transformations themselves, the XSLT transforms. Maybe those transformations are slow, and we could optimize them. So we did that. Again, made some small changes, pushed them through into production, ran some tests, and we came down to about 3.5 seconds. This is better, but it's still not 1.5. And then back to our original two options, which was caching. But again, which option are we going to choose? Well, we actually chose to put a varnish cache in front of our content rendering service. So it would cache the HTML that was the result of XSLT transforms, not just the raw XML from S3, which would be behind. So in this case, we saved the transformation time and we saved the fetch. And when we did that, we came down to about 0.2 seconds, which is okay, which is good. I mean, that was admittedly in the building. It was a bit more outside the building, but hey, whatever. Yay! SpongeBob. This is coming back now to how I think about these options, how I think about how software architects, the software architecture of our systems evolve over time, the things that are hard to change. Back to this idea of evolving down these different paths and making decisions. So we went down one path. We created this service to transform our content. We came to a point where we thought, can we add a cache? And at this point, we got a fork in the path. Do we add a cache in front or behind to save one or both of these different latencies? Back to the story. Content trickles into the store. You keep up by listening for the new content and casting wuget on the cache to keep it refreshed. New types of content appears. Content the villagers have never seen before. Content the walking skeleton is unable to combat. Every time the structure of the content changes, the cache must be refreshed. The cache grows and grows until it is big. It is no longer possible to refresh it. Latency increases. You have died. Turn to page 1. So we hadn't taken something into account here. We were under active development of the API delivering content to us. And every time we made a change to that API, which was frequently because we were continuously delivering changes into production, every time we made a change, the cache had to be blown. And that's fine when you've not got that much content, but when you get to gigabytes and then terabytes eventually in production of content, that's not so cool. In fact, what we've done is hit one of these evolutionary dead ends, much like the Regalo Wing in the Apollo program. But how much actual money had we spent? How much had we spent placing that bet? Not a lot. Adding a varnish cache is pretty straightforward, right? It's standing up a couple of machines, it's writing some Ansible scripts, and then provisioning them. Pretty straightforward. So I mentioned at the start that these books are a gateway drug to Dungeons and Dragons. One of the fun features about these books that I remember was that you'd always put your thumb or finger in the last page you were at after you'd made a choice, in case it went badly wrong, right? Kind of get the idea. So in this case, I'd be like, I flip back and I want to do the other thing now. In the same way that these books are gateway drugs to Dungeons and Dragons, actually sticking your thumb or fingers in the page is the gateway drug to version control. That's a weird thought. But all of this is under version control. We can do the equivalent of flipping the page back with our thumb sticking in the book, right? So we rolled back that change, and we re-implemented the cache somewhere else. We re-implemented the cache in front of S3. And the cost of doing that was tiny, absolutely tiny. And we progressed with the program. The cache causes the content load times to drop from 300 milliseconds or so to 150 milliseconds. The villager says, this is wonderful content is now blah, 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 and the story carries on. We have further choices to make as we evolve these systems over time. Further choices, further bets to place, further options to purchase. But I think that's enough of the story for now. So I guess to summarize, for me, software architecture is all about now, the activity of software architecture is about understanding the bets that we can place, the options that we have, and trying to decide which of those options have the most value. But then we have this set of techniques that we can use, right, that reduce the cost of those options, the amount of money we need to place as bets, even further. And a lot of these things are really new. And this is, I think, why we haven't really been doing this a lot. And this is not common practice even at ThoughtWorks, where we tend to be on the bleeding edge of things. But I think over time, this is where we're going to be going. The ability to make really small changes to things that were hard to change previously, and to have these changes pushed automatically through into your production environment, version controlled, tested. I think this is kind of a game changer. So what do we need to do this? Well, I said we need to be able to observe nature, so instrumentation, telemetry, visualization. The ability to run experiments, so lightweight probes for fun and profit. And we need to be able to rapidly change all the things, not just the things we normally rapidly change. So things like being cloud native and continuous delivery for infrastructure. I guess to reiterate, evolutionary architecture, I think, keeps our options open. It provides us the ability to explore the whole solution space by making small steps forward. Continuous delivery, lean product engineering, and infrastructure as code, they reduce the amount of money we need to place the bet. We don't need to bet the house anymore on a certain outcome, on an uncertain outcome. And this idea of running lightweight experiments, they allow us to make these guesses effectively and test our hypotheses. And with that thought, I'm going to say, it's beer o'clock. Woohoo! Thank you very much. I can take questions, but just catch me downstairs or something instead. There's a party about to happen. So.